Thank you for the introduction. This talk today is going to be about the ASCETIC Project and how we're trying to overcome energy efficiency problems in cloud computing environments. So the outline of the talk that I'm going to give you today is quite short. It's basically going to look at the background and the problem surrounding energy and energy consumption in Europe, and then present the ASCETIC Project, its architecture and potential solution to this problem, and then some future directions on where we'd like to go in the project. We've just done our second year review about 2 weeks ago, so we're in the third year now. So a bit of background. Energy efficiency is at the heart of the EU's 2020 strategy on basically making a more sustainable, smart economy. And energy efficiency itself is increasingly becoming important in the future of the ICT industry itself. Why? Increasingly we're seeing adoption of cloud computing solutions such as Office 365 and other types of software. And basically the energy costs for running these cloud solutions is continuing to increase. And with the increase in the use of these solutions, the energy costs, we have the issues surrounding the CO2 emissions and potentially global warming. So if we look at predictions in the growth of data center use and the power that they consume, we can see that at the moment there's a gradual trend in the increase of data centers to use more and more energy. So if we look at this graph, we can see that there's between a 4 and 5 gigawatt increase in the energy consumption of data centers. And as we try and extrapolate this into the future, we will see that this is going to continue to increase. So if we try and put that 4 gigawatt figure into some sort of perspective for us all, because it's quite a large number, basically the ICT industry is approaching 2.5% of the global CO2 emissions. And we're basically seeing that that's equivalent really to the global aviation industry. So that's a really big number. And we can see that with the current trends that this is going to increase even further by 3 or 4 times by 2020. So this average yearly increase of about 4 gigawatts is the equivalent to having to bring online the largest, a new coal-fired power station every year. And we can basically compare this. There's right close to where I live, there's a power station called Drax, which is the largest in Europe, and it basically generates about the same amount of power as that we need to in the IT industry. So how can we sort of start looking at the problem of energy consumption in data centers as a whole? Well, the first place to start is looking at where energy consumption goes in data centers. So the majority of this is consumed by the tens or hundreds of thousands of physical machines or hosts that are inside the data center, with 50% being attributed to servers and storage, with the rest of that being attributed to air conditioning. So how can we go about reducing this? This is enter ASCETIC, the ASCETIC Project. We're basically a European project that's looking to provide novel methods and tools to support software developers in minimizing the cloud and its applications' energy consumption. So we're a consortium of 9 different partners. Atos is the project coordinator, and Leeds, where I'm from, are the scientific and technical coordinators. And we have a few partners that have interest in specific aspects of this problem. So the approach that we're taking in ASCETIC is that we want to try and support energy efficiency across all layers of the cloud stack. So on the right hand side you see the traditional deployment model of clouds. We have infrastructure as a service, platform as a service, and software as a service. Our project is interested in how we can first make these layers energy aware, and then secondly how we can go about optimizing them to improve their energy efficiency. So we're going about identifying missing functionality in the software development processes within these layers, and looking at existing developer tools and how we can improve upon these. And basically we want to define and integrate energy requirements into cloud application software design methodologies. So primarily looking at the software as a service layer, and we see that this is really where the key novelty of our project lies. So the solution that we've come up with now that we're in the third year of our project is basically a reference architecture that integrates energy efficiency into service construction, deployment and operation, which we think is leading towards a more energy efficient embedded software lifecycle. And we're doing this through implementing our architecture via an open source software toolbox. And the key benefits of this toolbox, which you can see the architecture on the right hand side, I'm sorry for it being slightly cut off, are interoperability with existing standards. So we make use of OVF, as well as leveraging standard sort of de facto tools. We use OpenStack in our infrastructure layer, as well as using Zabbix, which I see they've got a stall here. We use Zabbix for our monitoring system. And the key benefits of the architecture are this idea of inter and intra-layer self-adaptation. So we want to go about optimizing the energy use of the different components and tools that are in this architecture, and do that by having a self-optimizing or autonomic system. So with that in mind, and given that I've got quite a short time for the presentation, I just wanted to give you a quick demonstration with a video of the infrastructure layer, where we've been doing some work this year on optimizing the deployment of virtual machines within infrastructures. So the video that I'm about to show you basically takes our use case from the project, which is a news asset application developed by ATC, and we've seen that there's a day-night cycle in its resource consumption. So we've taken that on board and developed a virtual machine manager that can manage and schedule the virtual resources of this use case and consolidate the resources onto single machines when they're not used. So I'm going to present a demonstration here that does live migration of virtual machines for purposes of consolidation. So if I start the video off, we can basically see that in this dashboard we have our application deployed, and we have this application is comprised of a number of different components that are contained inside virtual machines. Basically we're going to look at one of these virtual machines in detail to see how much energy this virtual machine is using. So we're just going to take this ID and have a look at how much energy this virtual machine is using at the moment within our Zabbix dashboard, which we've integrated into our architecture. And you can see in a second, after we've selected the appropriate virtual machine, we have capabilities at the moment in the ASCETIC toolbox to attribute power to virtual machines running on a host machine. And we can see at the moment that we're using roughly between 20 and 30 watts of power for this virtual machine. If we go back to the virtual machine dashboard, you can see that at the moment, the writing is probably very small, but these virtual machines are distributed across a number of host machines. And what we're going to try and do is select a more appropriate scheduling algorithm to try and reschedule these virtual machines that are spread across our infrastructure onto a single host, under the assumption that it's nighttime and our application is no longer being used. So maybe we can do this to reduce its energy consumption. So we triggered self-adaptation or optimization of the system, and we're at the moment live migrating these virtual machines from a distributed environment into a single host. And you can see now that all these virtual machines are on a node called Wally 153, and that if we go back to the power graph, that after the live migration and the consolidation of these virtual machines for this application, we've got a reduction of about between 20 and 15 watts of power. So that demonstration, excuse me, trying to find my slides again. So that demonstration sort of highlights some of the optimization strategies we're taking within our architecture at the lowest levels. If we look into the future in the third year of the project, basically we want to start looking at self-adaptation or the optimization of our architecture in between the layers. So at the moment we only consider the infrastructure layer and optimizing that, looking at platform services and how we can optimize those, and then the software layers. But how can you go about optimizing all these layers together for the purpose of reducing energy consumption? We also want to look at integrating the use of IPMI monitoring, because at the moment a lot of our architecture relies on having meters plugged in directly into machines to take measurements. And then finally, we want to explore energy-aware software profiling at the SaaS layer in more detail by continuing to develop our Eclipse plugin that looks at how you can attribute power to lines of specific code within your application. And hopefully this will give the ability to developers to identify energy hotspots within their applications and optimize their code, not just for performance, but also energy efficiency. And with that, we're sort of starting the optimization process a lot earlier than is done in business and in the real world at the moment. So one concluding remark before I finish. Will energy efficiency benefit the environment? So if we have the ASCETIC solution, people start using it, will it actually be any good for reducing greenhouse gases? And in my opinion, rather, probably not. And one of the reasons for this is that William Stanley Jevons, who was an industrialist in the UK, who developed basically some technologies to improve the access to coal, found that with improved efficiency came increased consumption. So I think that's something that we're going to have to deal with as we improve the efficiency of our systems as a whole. So there's nothing to say that improving the efficiency won't mean that we can't do more with what we already have, but I think we also have to be careful that we don't continue to consume.
Same for the roads. You make bigger roads, you get more traffic.
Yes, exactly. So that's the end of my talk. Thank you very much. Are there any questions?
Thanks a lot. Are there any questions?
One question?
I have one question. I mean, part of the motivation for going to cloud is to share machines with other users, so that you are not keeping a lot of idle machines running, and knowing that the power supplies of the machines are consuming quite significant power even when idle.
Yeah.
Then there is a question, how much is actually increased in global power consumption because of cloud usage, as compared to having all these half-full machines running all around in different companies?
Yeah.
Have you any idea about that?
Yes, so when we first started the project, we looked into this problem, and we found that the utility of normal non-cloud systems is between 10 and 30%. So the cloud can improve upon that by consolidating workloads. It's one of the primary principal benefits of cloud computing. But at the same time, doing that, you also have to consider the performance ramifications and the interference of running different workloads as well, which is something else that we also consider, which I haven't had time to discuss in the ASCETIC project. Hello.
Very interesting work. I'm curious about how you can accurately measure the power consumption of each individual virtual machine.
Yeah.
Given the current, the architecture of the machine, it's relatively easier to give an estimate or measurement of the entire physical machine.
Yeah.
But for each virtual machine, it depends on its activity and resource consumption.
So it's a very, very interesting question. So a lot of our work is related to modeling virtual machines' energy consumption, and basically the approach that we've taken is that we measure the consumption of a physical machine, and then we have a model that attributes the resource consumption of that physical machine to specific virtual machines. So we can say that, if this virtual machine is using 1 out of 8 available cores, then maybe we can partition 1/8 of the power. I'm not saying that that's always 100% correct, but we can get closer to a more approximate value for the energy that's being consumed on a per virtual machine basis. So we look at different things such as CPU, memory, cache, disk, network, utility, and then we have a model that we push these utility values into to give you the virtual machine energy consumption, or power consumption rather, in real time out the other end.
Because if physical books.
Yeah.
But sometimes the machines can mount external resources such as cloud storage.
Yeah.
And does your models have
Ye-
any consideration about that?
Yes. So the architecture that I presented has a distributed file system and software-defined network element to it, where we basically monitor these systems and see how the virtual machines are making use of them. And at the same time, we see how much these like auxiliary systems are consuming. So maybe the distributed file system comprised of a cluster of machines is being used 2% by one virtual machine. You can maybe attribute 2% of its power consumption to that virtual machine. So that idea is more related to the sort of the billing side of trying to attribute different subsystems within the cloud to a specific virtual machine. But yeah, a very interesting question and something that we definitely tackle.
Have
Yeah.
any cloud vendors adopted your software to enhance their billing?
No, not currently, but that's something that we're working towards. At the moment, we base our solution on OpenStack. So our virtual machine manager, which I presented in that demo, sits on top of OpenStack and is a value-added service. And what we're trying to do at the moment is push that into the OpenStack ecosystem as an add-in that people can download. But we're finding it quite difficult actually to get around the bureaucracy of some of the OpenStack guidelines on community contributions. But hopefully we'll be able to work through that before the end of the project, and people will be able to use our software. So thank you very much.
Thank you very much.